Yeah, it's a great pleasure for me to be here for this final conference about time and setting time right. So you see here time occurs here twice in the title, Arrow of Time from Timeless Quantum Gravity. So I actually have to show two things. I mean, why quantum gravity is timeless and why this helps, in fact, to understand the emergence of the arrow of time in usual situations. We have already heard a lot about the arrows of time. Here I can be brief. I think here is the introductory part, arrows of time. So almost all the textbooks, laws of fundamental physics, they distinguish, they do not distinguish a direction of time. They are time reversed invariant. But we observe classes of phenomena in nature empirically that distinguish the direction of time. And the most important so-called arrow of times are the radiation arrow. We use retarded potentials and not advanced potentials. Thermodynamics, the second law. Quantum theory, the measurement process, in spite of the Schrödinger equation being time reversed invariant, the measurement process, emergence of plasma distinguishes the direction. And finally, gravity, in its aspects of having formation of structure, gravitational collapse, in the extreme case, collapse to black holes, and the expansion of the universe, which distinguishes the direction. And the question is there a master arrow of time behind it? Is there one physical process that is responsible for all these arrows pointing in the same direction? And we already heard about it here that the most likely the origin can be traced back to cosmology. Gravitational collapse leads to the fact that we have actually hot spots like the sun and stars in an empty space, and this of course gives rise to a possibility that here on Earth and life has developed and so on, that we have a state of low entropy, that we are far away from equilibrium. So, but where does the sun come from? From gravitational instability of dust clouds, and this eventually leads to cosmology. Here is a famous quote by Boltzmann. So in my literal translation, he wrote that in nature the transition from a probable to an improbable state does not happen equally often, as the opposite transition should be sufficiently explained by the assumption of a very improbable initial state of the whole universe surrounding us. So it's just the idea that, of course, you have an eternally existing universe, infinitely large. There's a small chance that a gigantic fluctuation occurs where all of us, including our memories, emerge. Now, this argument was criticized later by various people. Weizsäcker in 1939 made it very explicit in response to this Boltzmann's papers. He wrote, again in translation, the straightforward application of probability calculus to this world view leads to unacceptable consequences. For it is indeed statistically much more probable than that all these documents have emerged by fluctuation than that the preceding states of lower entropy, which we infer from them, had indeed been realized. But what Weizsäcker did not take into account is, of course, there are subtle many correlations in the documents that we observe. So it would be much more unlikely, certainly, to have a macroscopic world with inconsistent documents, where you go to the bookshop and find books just like in Boyle's Library of Babel with no meaning. So it would even be more probable that, as we also have heard here, Boltzmann brains, for example, popped into existence, would observe an empty world around them and no documents. So what I infer from all this is that we should take seriously the idea that the universe really evolved from a low entropy initial state. So this is past hypothesis, and that there are no these arguments about the fluctuations just show pointing to this direction. So, given that, how can we understand it possibly in physics without just postulating it? Let's have a look first at the order of magnitude of the entropy in the universe. So, non-gravitational cosmic entropy, one can estimate, is dominated by the cosmic microwave background photons, and they add up to 2 times 10 to the 89 in units of Boltzmann's constant, which is said equal to 1 here. This you should compare with the gravitational entropy, but alas, we know that there is no generally accepted expression for gravitational entropy. The only concrete formula we have is the Bekenstein-Hawking formula for the entropy of black holes. And this is written down here, so it's the area of the event horizon in terms of 4 times Planck mass, Planck length squared. Now, estimates give the following. For example, our galactic black hole, which is a supermassive black hole of 4 million solar masses in the center of our Milky Way, already gives 6.7 times 10 to the 19. So already this one black hole has more entropy than all of the non-gravitational entropy of the universe. And if you estimate all the contribution of all supermassive black holes together, so this is from a recent astrophysical paper, then you get this number 3 times 10 to the 104. Now, if all of the mass in the observable part of the universe were assembled into one gigantic black hole, you would get an immensely higher number, namely 10 to the 121. So this is calculated on the basis of Schwarzschild de Sitter space-time, where you have a black hole in a universe dominated by a cosmological constant. And if you asymptotically assume de Sitter space, empty de Sitter space, you would even get a higher entropy, given Hawking entropy, which is 1 over cosmological constant Planck length squared, and which is 10 to the 122. Now, Roger Penrose in 1981, he made a well-known estimate about the probability of our universe, which is given here. I updated it with the present observational numbers of cosmological constant and so on. Which means that naively you have the entropy of the universe, so you have e to the s as the probability divided by e to the maximum entropy. Now, this 10 to the 104, recall this is here, this contribution by all the supermassive black holes, which is much higher than the cosmic microwave background. And as max, I have taken here this number, 10 to the 122. And so you get this incredibly small number, which is so small and so tiny that it really demands an explanation. It cannot be just there by chance. So our universe is very special indeed. Now you see here the 10 to the minus 104 is completely negligible compared to the 10 to the 122. Now, where does the explanation come from? If it has to do with cosmology, so with the origin of the universe, and certainly with then a phase where quantum effects should not be neglected. So the hope is that the explanation could perhaps come from a fundamental theory of quantum gravity. Now, quantum gravity, of course, as you know, there is not yet any final theory available. There are various approaches. But what I try to explain here is that at least from a very conservative approach, where very close to standard physics, tentatively an understanding is possible. So how does this happen? Now, let me make a jump to history, to Schrödinger, to one of his famous papers where he introduced his wave equation. And again, in translation, what he wrote there in 1926 is, we know today, in fact, that our classical mechanics fail for very small dimensions of the path and for very great curvatures. Perhaps this failure is in strict analogy with the failure of geometrical optics. That becomes evident as soon as the obstacles or apertures are no longer great compared with the real finite wavelengths. Then it becomes a question of searching for an undulatory mechanics, and the most obvious, so this is the important part, the most obvious way is by an elaboration of the Hamiltonian analogy on the lines of undulatory optics. So what he did is he rewrote mechanics of a particle in Hamilton-Jacobi form, and from this he guessed a wave equation that gives back classical mechanics in what we call the WKB limit. So he guessed his wave equation just from what we say the semi-classical limit. So this is sketched here. So from the mechanical Hamilton-Jacobi equation, you can guess the, in this case, the non-relativistic Schrödinger equation. So let's do the same for gravity. Let's be very conservative and just follow this rule. When we have a well-established classical theory of gravity, which is Einstein's theory of general relativity, so rewrite general relativity, the Einstein equations in Hamilton-Jacobi form. This is what Achaperes did in 1962. And then just from this follow Schrödinger's root and guess a wave equation that gives back Einstein equations in Hamilton-Jacobi form. Yeah? So just follow the very same route, no additional assumptions, just assume that standard ideas of quantization are correct. And this then leads to the Wheeler-DeWitt equation. And there's some confusing literature about the meaning of this equation. Sometimes you read, okay, this is a kind of old-fashioned approach, an alternative to strings that has been outdated. This is not true. Yeah? Wheeler-DeWitt equation is not just an alternative route to quantization. It's what you get immediately from making the first step out of the classical theory into the quantum realm. It's not, most likely not the final theory of quantum gravity. Perhaps will be superseded by loop theory or by string theory, but it should be reliable, if quantum theory as a whole is correct, should be reliable in the same way as the non-relativistic Schrödinger equation is correct. The non-relativistic Schrödinger equation is also not the most fundamental equation. It does not capture quantum field theory, but you get a lot of information, a lot of empirically testable predictions. If you think just at the hydrogen atom, if you have some appropriate boundary regularity at the origin, in spite of the fact that at the origin you have quarks and gluons, whatever, you get the correct spectrum. So this is the Wheeler-DeWitt equation. Here are Wheeler and DeWitt. And here's again the question, what if you just ask the question, actually this was Wheeler's question, if you like, what is the quantum wave equation that immediately gives Einstein equation semi-classical limit? And this is the Wheeler-DeWitt equation, which is of the form h psi is equal to 0. So we have a quantum state that, as far as gravity is concerned, depends on the three-dimensional geometry, not the form, but the three-dimensional geometry. And it's annihilated by the full Hamilton operator of gravity plus all non-gravitational fields. And the point is that you get such an equation from any theory that is classically invariant under time reparameterizations. So whenever you have a classical theory devoid of an absolute external time, in the quantum theory you get such an equation where the t, the external t, is just missing. Yeah? It has disappeared. And it can be understood intuitively. I think Wheeler has explained it here, the blackboard. So if you go to mechanics, you have here classically a path, a trajectory, but in the quantum series you just have a wave function depending on configuration space. Now in mechanics and in quantum mechanics, in addition, you have the external time t, which is just there and which is not influenced by anything. In gravity there's no external time. So if you just do the same for gravity, this corresponds to a space-time, and this just corresponds to spaces, configurations of spaces. So the configuration space, Wheeler's superspace, is the space of all three geometries. And so as particle trajectories have disappeared in quantum mechanics, space-time has disappeared when you just very conservatively quantize gravity. An equation of this type also occurs or arises in loop quantum gravity, for example. So it's certainly not special to the Wheeler-DeWitt equation, just that the explicit form is different. And this is what gives rise to problem of time. There is no external time anymore, so you have a stationary wave, h psi is 0, there is no d over dt here. This also holds for loop quantum gravity and probably also for string theory. I could say something about that if time allows. If you look more closely into this equation, which I have not written out here explicitly, then what you see is that this equation has an interesting structure. It is what we call a hyperbolic wave equation. That is, you have a kinetic term where one part of the kinetic term has a different sign from the other, like with the oscillating string and so on. So, in spite of the absence of t, this could give rise to intrinsic time-like variable constructed from space. And in typical examples, it's just the size of the universe, the scale factor, or the volume of the three-dimensional universe, which is an intrinsic time standard. There are other problems which time does not, our seminar time does not allow to discuss. The input space structure in quantum mechanics, which is connected with the probability interpretation, and in particular the conservation of probability in time. It's unclear what will happen with such a structure if there is no time t, because what does it mean to talk about unitarity and conservation of probability if there is no time t? There are some quotes. I mean, John Wheeler in his famous Bataille rencontre article from 1968, he was, of course, fully aware of these consequences, as were also other people before him, like Dirac and Bergman, who studied canonical quantization. He wrote, these considerations reveal that the concepts of space-time and time itself are not primary, but secondary ideas in the structure of physical theory. These concepts are valid in the classical approximation. However, they have neither meaning nor application under circumstances when quantum geometrodynamical effects become important. There is no space-time, there is no time, there is no before, there is no after. The question what happens next is without meaning, at this fundamental level, of course. Weiss de Witt was very critical about this equation later, but of course he understood fully the consequences, so he wrote in 1999, one learns from this that time and probability are both phenomenological concepts, valid only in the semi-classical limit. An example. It's often said that a real grid equation is mathematically undefined. This is, well, not really true in the following sense, because if you write down it in full, in the so-called functional Schrödinger picture, of course there are mathematical problems, but these problems are on the same footing as, for example, in quantum chromodynamics QCD in the Schrödinger picture. But in the QCD you can go to parts integral, you can make perturbation theory and so on. Here you can also do that, for example, dynamical triangulation, Recce calculus. These are methods that are equivalent to the relativity equation, try to put it on a firm footing. Moreover, in simple models like cosmology, there are no mathematical problems. So this is very simple. The Friedman universe, which is a genius, isotropic universe, and it has only the scale factor as its variable, and to make it non-trivial, I add a matter field, a homogeneous scalar field phi. So we have a two-dimensional superspace, and because only two dimensions of mini superspace. The classical line element is given here, the S squared, so we have the form with the left trunk, which just gives the reparameterization invariance of T, the classical T, and here you have the scale factor, I assume a closed three-dimensional universe. And then the equation here, I wrote it down explicitly, so you have a kinetic term, you have a potential term, and you have H, this is the H, on psi is equal to 0. So this is two-dimensional timeless quantum mechanics. And you see here from the kinetic term that the term with respect to phi has its usual sign, namely the minus, as in Schrödinger's equation, but that here the term with respect to A has the wrong, or the other sign, the plus. And this gives rise to all the non-trivial features. Already at this level you can see important consequence of the concept of time, a consequence for the concept of determinism in the classical and the quantum theory. The classical theory is here shown at the left, so we have this two-dimensional configuration space of the scale factor upwards and the scalar field rightwards, and classically say at the computer you put here some initial conditions, and then you get here the solution. You could equally well do it here, so there is no absolute direction, but the important thing, there is a trajectory in the classical theory. So in this sense, the recollapsing part is a deterministic successor of the expanding part. But if you have just a wave equation without t, without trajectories, the wave equation, which is displayed here, how would you proceed if you did not have any prejudices? What all this means? Of course, you have a wave equation in a phi space, and it's a hyperbolic equation. So what you do is you go to hypersurface of constant A, A plays the role of intrinsic time, you put your initial conditions there. And if you, for example, desire to construct wave packets that follow the classical trajectory as good as possible, then you would have then to put two wave packets here simultaneously, because here are your initial conditions. A quantum equation does not distinguish intrinsically between ends of a classical trajectory, because there is no classical trajectory. So you have to put the recollapsing packet into your initial condition. Yeah? And then you can make the calculations and you can hope to get in the concrete models wave tubes following the classical trajectory, but there is certainly no arrow here and no direction in this. If you did not choose here the second part, you would just get a fully smeared out solution. You would not get any hint of classical behavior. So the recollapsing wave packet must be present initially, and this is a direct consequence just of the equation, just taking the equation seriously. Now 2 dimensions, this is of course insufficient to explain the emergence of structure, to explain the error of time, for which you need thermodynamic degrees of freedom and so on. So in principle you should go to the full equation, but this is difficult, of course. What you do here is to make to add small perturbations to homogeneity. That is, you have your 3-dimensional sphere, the 3-sphere, and you add these modes with very small and wavelengths. And these are called here the multipoles and symbolically denoted here by xn, where n is a complicated index. You can use stereo harmonics for that, but that's not important here. And then you have h psi equals 0, you have the mini-superspace part just displayed as transparent, and you have here the sum of all these modes, which at the lowest order just decouple and only couple to A and phi, and you have this capital wave function, this capital psi equals 0. So this is what Halliwell and Hawking did in 1985 in their paper on the origin of structure in the universe. If then psi naught, I make this ansatz, psi is psi naught times the product of all this psi n, so if psi naught is of W form, which is this form here, then one finds, after calculations at highest order, that these psi n's, they obey an approximate Schrödinger equation, where on the right-hand side you have these Hamiltonians n. But here time reappeared, so where does this time t came from? It just arises in the same way as in optics, light rays emerge from wave optics. I mean, there are no light rays in wave optics, of course, but you can have make an approximation, the Eikonal equation, and then you get light rays, where the light rays actually propagate in a direction nabla s, where s is the Eikonal. The same happens here. So this t is just an abbreviation for nabla s naught, nabla, and s naught is what is here in the exponent, and this nabla just means nabla in configuration space of mini superspace. So with respect to the scale factor, or alpha is lowest of the scale factor, and phi. So you get here an approximate Schrödinger equation from a special ansatz. It's not generally valid, and this time t is then called WKB time, is the time that controls the dynamics in this approximation. And this is nothing else than the limit of quantum field theory in curved space-time, retrieved as the first approximation from timeless quantum gravity. Now, of course, in quantum gravity, in quantum cosmology, if we assume the superposition principle to be valid, and so we have again superposition of different metrics. So in the attempt to interpret the situation in quantum cosmology, we investigated the concept of decoherence there already in the 80s. And so system and environment, of course, is not something internal and external to the universe. It's just something in configuration space, a relevant part and an irrelevant part. And the idea was to take, say, scale factor and inflaton field as relevant parts and say small gravitational waves as irrelevant parts that you have to take into account. They're in these multipoles, but you have to trace them over because they're not observed. So, for example, you get the following result. So, in this early papers, we just used the cutoff in this infinitely number of modes. We just made a cutoff at a Planck scale. So later, with my Russian colleagues in '99, we thought about a more mathematical regularization procedure. But anyway, one example is that if you assume semi-classically de Sitter space, so A is proportional to e to the ht, hi is constant, and this is the system, and you have gravitons on top of it and have interaction, and then this is decohered by the gravitons according to this result that the initial density matrix, which is fully quantum, corresponding to state, gets multiplied by such a Gaussian factor, which you see here has a minus a prime squared here, so it suppresses the off-diagonal terms which are responsible for the interference terms between different three geometries. And you see here, because the A appears here, that the bigger the A, the smaller this becomes. And if you insert numbers, you see that the universe assumes classical properties at the onset of inflation. So in a sense, inflation also, if it's there, solves the classicality problem, not only the hierarchy problem. Of course, we had to assume certain initial states, otherwise you would not get this, and the initial state was that all these fluctuations are in the adiabatic ground state initially, as close as possible to a cone. And you see already here, and make it clear at the end, I mean how the error of time in this sense will appear. There's of course an issue because here this is a special ansatz. Here is e to the I s naught, and as Julia for many years rightly emphasized, this is of course a particular ansatz because it puts in the imaginary unit in the context of a wave equation which is real. So where does the imaginary unit came from? So in '93, each of us, we have two papers in physical review, one of the other where we discuss this problem and where we point out various solutions. And the solutions I like most is again coming from decoherence, and because it's a very strict analogy to what we know from molecular physics. In quantum mechanics, you have also an invariance, a parity invariance, the Hamiltonian parity invariance, so there is no mirror asymmetry, but for example, for chiral molecules, we observe breaking of this symmetry. So these bigger molecules, they are chiral. And in molecular physics, we know how this happens. So you have here a superposition of, say, two chiral states. The eigenstates of the Hamiltonian, of course, they are smeared out about both potential wells. So this is the ground state and the first excited state. But the observed molecules, the states are localized either here or here, which are superpositions of ground and the excited state. And we know that we can calculate this from the interaction with photons and air molecules. Chiral molecules are optically active, so there's a strong coupling to photons, and this leads to decoherence, so symmetry breaking. And the same also happens here if you do the calculation. You could start, if you wish to do so, with a superposition of the e to the is and e to the minus is, then you have a perfectly real wave function, but the interaction, for example, with gravitons and others distinguishes between the two components and not between other components. An example I calculated long ago was that for our present universe, if you put in some numbers in a model, then the off-diagonal term between these is very small. This means with this accuracy, you can really assume our today's universe to be classical and quantum gravity or quantum cosmology effects to be negligible. Once the background is classical, you can also start to think about the origin of structure in the universe, how the quantum to classical transition happens with the fluctuations on top of it. Yeah? Inflation produces fluctuations, they are quantum, the primordial fluctuations are quantum, but what we observe in the microwave background are classical stochastic fluctuations. And this can be understood, it's not my topic today, but it can be done. Again, on the basis of the decoherence according to other fields or to inhomogeneous other fluctuations in the non-linear level. And typically in inflation you have decoherence time. The exact result is more complicated, but basically it's given by the Hubble scale, h to the minus 1, which is in the basic of this type. So this is the decoherence scale for inflation. So in a couple of papers, we basically with Polaski and Salvinski, we did some explicit calculations. So also the fluctuations themselves assume classical properties during inflation. Now the error of time, setting time right. So I should of course address the question of the conference. And how could it come? Well, at the beginning I mentioned that the fundamental laws as we know them today in written down textbook, they are time reversal invariant. So reversal invariant t going to minus t. Now for the first time you have a candidate for a fundamental equation which is asymmetric in the following sense. So look at the Wheeler-DeWitt equation h psi equals 0. So here again you have the part with the scale factor, this is the alpha square, and here you have the fluctuation part, and here you have the potential which covers the size of the universe with all these nodes. And if you closer inspection leads to a surprising discovery that this potential goes to 0 if alpha goes to minus infinity. Alpha is the logarithm of the scale factor. So this means as a, the scale factor goes to 0. This is what we call the Big Bang. So this equation becomes very simple for small a, but very complicated for large a. So you might say, well, but it's on the basis just of these fluctuations. We have to study the full equation. This is of course correct. It's too complicated, but there is the so-called BEKL conjecture, the descent of Belinsky, Kalashnikov-Lifshitz, which found out in the classical theory that spatial gradients become more and more irrelevant as you approach the Big Bang. So that space, so that different points in space decouple. Yeah, and so this is reflected also in this approximation. So the equation becomes very simple. And it becomes complicated for bigger A, and it's certainly not invariant under alpha going to minus alpha or something. So for small alpha, you could impose the following initial condition, which could be related in according to David Wallace's talk yesterday as the par-simple hypothesis, yeah, because it's a very simple solution, which is just a product state with respect to all variables, an unentangled state. You know, it's just psi naught times psi 1, psi 2, and then everything else just depends on its own variable. And if you plug this in, because the potential becomes stronger and stronger, you automatically get an entanglement with respect to alpha. So the entanglement entropy, if you take this as a candidate for entropy, the entanglement increases with increasing scale factor, since entanglement with other degrees of freedom entangled. And in the semi-classical limit where the t is present, this defines then automatically an imprint at the rate of time on the t. Of course, in general, there is no t, and this is just the equation, but in the situation where you have the semi-classical approximation, then such a boundary condition and its ensuing increase of entropy for alpha would also give an error of time for t. So this is where the asymmetry, the error of time outward, how this could arise from those timeless equations. It's in an indirect way, but in a sense in a very straightforward way. Here's our two pictures. So I guess almost all of you know Penrose's Weil tensor hypothesis from 1979, where he emphasized this asymmetry between Big Bang and Big Crunch. Let's assume we have a recollapsed universe. There's no observational evidence at the moment, but for the model I think it's fine. So entropy at Big Bang is very low, so very smooth, Weil tensor is vanishing, but then you have this emergent structure, these stalactites in the conformal diagram, and so the Big Crunch would be extremely inhomogeneous, Weil tensor would be diverging. And so the Weil tensor hypothesis actually is an hypothesis that demands for an explanation in quantum gravity. but the picture looks drastically different if you take into account quantum gravity in its most in its simplest form, because as we have seen, the wave function only knows about small scale factors and large scale factors. The wave function doesn't know about ends of classical trajectories. In ordinary quantum mechanics, no one would think about a wave function depending on some trajectories, because they're not there. So Big Bang and Big Crunch in configuration scheme are the same. And if you impose a low entropy condition at a Big Bang, in quotes, of course it also holds for the Big Crunch, because it's just a region of small a. So you would get, instead of this highly asymmetric picture, you would get a highly symmetric picture. You have here radius 0 and radius 0, so structure emerge, but here formally you would have a time reversal. That is, entropy would always increase from 0 radius to maximum radius, so you would have a direction of time from here to here and a direction of time from here to here, and the whole scenario is consistent because it turns out that here in the middle you would just have an interference effect, so you would have a full quantum region, so there's no classical causal connection between the two branches, and all observers would only see expanding universe. So this may be correct, this may not be correct, but what I emphasize is that it's a consistent conclusion that you can draw from the equations. I mean, this is what I do here, just taking the equation seriously. Of course, there's the multiverse, and I perhaps cannot say much about this. This could also be, of course, topic for further discussion. Quantum entanglement, at least, is not limited to sub-horizon scale. It's already the case in the inflationary scenario. So it would be surprising that you would have a total quantum state which is a product state of all these various subparts. So you should have, I would expect the same error of time everywhere. Linde and Manchuri have estimated, for example, the number of local Friedman type universes in the context of inflation, which they estimate by the stronger e to the entropy of the perturbations, and n is the number of e-folds of inflation. And in the simplest model of chaotic inflation, we get this number which certainly no one can really grasp intuitively. And in the case of the string landscape, this number would be even higher. But nevertheless, I would speculate that even in that context, these ideas in principle could be applied. Now I come to the end, the conclusion. So the idea was to derive the master error of time from quantum gravity. And I have argued and tried to convince you that quantum geometric dynamics, which is the equation framework, and probably also quantum gravity, could provide the necessary framework to do that. I mean, in a separate talk, I could explain in loop quantum cosmology with a discrete equation how this happens and how this is done. It's not different in principle. The error of time could then arise from increasing entanglement, increasing decoherence out of a simple and natural initial condition. And along this, already this has far-reaching consequences for at least classically recollapsing universe. It shows also that if you do quantum cosmology, say quantum gravity, so quantum effects are not a priori restricted to the Planck scale, as some people claim, because the Planck scale is a scale in the equations, but quantum theory is universal. So all the classical domains probably should be understood from the equation and not imposed by the physicist. An interesting question, this is a speculation already done by de Wit in his pioneering paper of 1967. Is there a unique class of solutions to H-primes, and if yes, does it implement a low entropy initial condition? Of course, this was just one possible. It's possible because of the structure of the equation. Initial condition very simple and natural, but of course you could write down others. And de Wit was speculated if once we understand the mathematical properties of this equation, that you have no choice then to write down a certain class of equations. Like the Schrödinger equation for the hydrogen atom, once you have your regularity condition that it should be normalized and that at the origin it should not diverge, you have a unique solution that gives leads to the understanding of the atoms and molecules. And if this turned out, then we would have derived the error of time from quantum theory. Yeah, I made some speculations to the multiverse, but I leave it for them, and I thank you for your